now we are going to delve into the world of the P version of the finite element method. So far we have looked at the H version of FEM, right? And the P version of FEM works remarkably different. Who remembers how it works?
Increase polynomial order?
We increase the polynomial order. So the idea is very simple. We reduce the error, we improve the approximation by just keeping our mesh fixed, but we increase instead the polynomial interpolation order. So this is the overview of today's lecture on the 𝑝-FEM. We're going to look at the basis functions that we're going to be using for 𝑝-FEM. And well, obviously, we're going to start, as always, in a 1D setting. So this entire lecture is going to be on 1D. The next lecture is going to be entirely on higher dimensions. So obviously, as we did it in elastostatics, in HFEM, everything that we learn in the 1D setting translates nicely, except for some caveats here and there, to the higher dimensions. So those caveats are going to be slightly different when it comes to 𝑝-FEM, because as you will see, our P functions, or P shake functions, are no longer going to satisfy a Kronecker delta property. So we lose the so-called Kronecker delta property for the nonlinear functions. Linear functions, if we just look at them, they are going to keep the Kronecker delta property. Nonlinear functions are going to be exactly 0 at the nodes in the 1D setting. But now we are also going to lose another property. So the partition of unity property no longer holds in the 𝑝-FEM, right? So if we now pick a point and we sum all the functions, unless those functions are just simply linear, we lose our partition of unity property. So all those functions are not going to add up to 1. And so, well, after looking at the basis functions, we're going to do the same thing. We're going to look at the Galerkin projection and then some examples, okay? All right, say we want to go higher order, right? And then we just take these very simple bases of monomials. We plot them in our -1 to 1 interval because why? Yeah, that's basically our master element, and that's where we have defined our integration rules, as we just learned from the isoparametric formulation. But now we want to go higher order. So take a look at these bases here. I have c squared, c cubed, all the way up to 6 to the power 9. And notice that while one part of our subdomain remains strictly positive, the other one kind of alternates, right? But more importantly, what can you notice? What happens as I'm increasing the polynomial interpolation order in that direction? Not much. Yeah. Well, actually, that is exactly what I want to hear, right? Nothing much is happening, but can we say that in different words? What is happening? Diminishing returns. That's a beautiful way to say it. Seriously, I never heard that from anybody. That is basically the right way to say what is happening, right? If you notice, we have diminishing returns. In other words, as we increase the polynomial interpolation order, our functions are going to start looking alike, right? And that is good or bad? Huh? Good? You say good. Why? No, it's not good. But why is it not good?
Because they're like very parallel, so they're not really orthogonal.
They are really not orthogonal. They are almost parallel. They are basically introducing the same information. And the same information in our stiffness matrix is not good news, right? What is happening is that as we are using these bases, our shake functions become more and more close to one another, introducing some sort of linear dependency between the shake functions. And that makes things very, very hard, because what grows in our problem? The condition number. The condition number blows. So as we increase the polynomial interpolation order, now the condition number blows up. It becomes very ill-conditioned to a point where, well, at some point we no longer are able to solve the problem anymore, right? So we discard these bases, right? Not good. This is not good. So look at this. This is a so-called Legendre polynomial basis. And one thing you notice is that now we don't have diminishing returns. every single new shake function that we introduce in the -1 +1 interval introduces somehow new information that we can use. And another way to say that is that all these functions are orthogonal to one another. What is orthogonality? Well, we can define orthogonality by using a very simple expression. So if we say that this is some sort of our dot product between functions, right? Imagine that the same way you have the dot product between your two vectors in Euclidean space, right? If the dot product between those two vectors is equal to 0, you can always say that those two vectors are orthogonal to one another, right? Well, this is the way we define orthogonality for functions, right? I'm integrating these functions in my domain of interest, right? In this case, it's going to be -1, 1. And then if the product of those two functions in that domain of integration, of course, I'm looking always at the integral, is equal to 0, then I can say that these two functions are actually orthogonal to one another. Well, the Legendre polynomials are orthogonal polynomials. So every new function that we introduce and every newer higher order polynomial is going to be orthogonal to all the bases that we had so far built. And so something nice about Legendre polynomials is that you can construct them very, very easily with this equation. It's some sort of recursive equation, right? So you say here that the Legendre polynomial of order p is equal to this whole expression, and then you see basically p showing up here. That is the polynomial order interpolation. But then you have p, this is the Legendre polynomial p minus 1, so one order less, and then here you have two orders less. And so now, obviously, p0 is going to be equal to 1, and then p1 is equal to c, and these in a way are the ones that are going to finish the recursion, right? And so because it is some sort of recursive formula, this is also super easy to code, right? It's very simple in any programming language to have these recursive functions that, of course, you need a way to finish the recursion, right? For which you have these two guys here. But it's very simple to implement that, and we're going to look at pseudocode or how to do this. Okay, so something also that is very nice is that, well, if in order to get my polynomial, Legendre polynomial of order p, right, I need the one p minus 1 and p minus 2, well, you can do also something smart, right, so that you don't have to recompute these things, right? If you cache that, right, you can always save on computational effort because you have already computed that. So you can say, well, if I now need to compute the Legendre polynomial of order 10, well, I know that I have already computed the 9th Legendre polynomial and the 8th Legendre polynomial at that location, and so I can reuse that computation. So it makes, in a way, simpler to, or you can save computational time because you can cache those expressions, right? Okay, and we talked about this. Computing a cubic polynomial can reuse linear and quadratic computations. We talked about that already. All right, so how do we work with these polynomials? Now that we have chosen a basis, yeah, all we have to do is to try to use them to our advantage. But let me ask you, if you remember the stiffness matrix, for instance, right? That involves the polynomials or involves the derivatives of the polynomials? The derivatives. And so, do we want the Legendre polynomials or we want the derivatives of the Legendre polynomials to be orthogonal? The derivatives. And that is a little thing that we do because what we want in the end is to make sure that our stiffness matrix is well conditioned, right? Our stiffness matrix. And our stiffness matrix was computed using the derivatives of the shake functions, not the shake functions themselves. And so now we apply this little, trick so that we make sure that the derivatives of the shake functions that we're going to define are actually orthogonal, right? Because if I can say that this holds, that this is equal to the Kronecker delta property, right? Remember that the derivative of this guy is basically multiplied by the derivative of that guy. So if this is a Legendre polynomial and this is another Legendre polynomial, right? And I know that if I is not equal to j right, this is going to be equal to 0 because of the property of the Legendre polynomials, because I know that they are orthogonal, right? But if I also make sure that whenever this function is the same, right, then the result of that computation is equal to 1, in a way I'm scaling, right, those polynomials, then I can guarantee that if I make that happen, then this result is going to give me the Kronecker delta property. And so this is the best case scenario for my conditioning of the stiffness matrix. It cannot have better conditioning than this, right? And so, well, let's build our shape functions. And the way the 𝑝-FEM works is I'm going to take my linear basis that I know from 𝑓EM, and I'm not going to ever touch that basis. This is going to stay fixed. And so you see that my first two functions are phi1, y minus c divided by 2. Phi2 is 1 plus c divided by 2. That is fixed. And from that point forward, I'm going to hierarchically improve on that basis. So now I don't touch the linear basis, I'm going to add a quadratic equation. The quadratic equation is not longer going to be touched. Remember, we're building these high order polynomial functions by reusing functions that we have already computed, right? And so my quadratic function is not going to change. It remains fixed. And on top of the quadratic, I'm going to have a cubic, and a quartic, and a quintic, and so on until I am happy with the polynomial interpolation order. So in order to make this happen, then it turns out that the expression of these functions that are the nonlinear ones, remember, these are the linear ones that I don't touch from 𝑓EM, that I'm going to enhance hierarchically. Now I'm going to be using new functions, and those new functions are computed in this way, just to make sure that this property holds, right? Like whenever I compute in the domain of integration -1 and 1 the derivatives of those functions, then I get the Kronecker delta property. So when you do that, this is the way they look. So notice that now, interestingly, my linear shape functions from 𝑓EM remain there. They are untouched. They are equal to 1 at that location. But now my quadratic function looks like this. It's negative. And then I have a cubic function that is there, right? Then I have the quartic function, and so on. So these are all the functions all the way up to polynomial order 9. And if you notice, those are the derivatives of the functions that, as I discussed, have to be orthogonal to one another. And again, they are scaled because I also want their product to be equal to 1 in the domain of integration. So these are the functions that we're going to use to build our 𝑝-FEM approximation, right? So once we have our basis, you have a question?
Yeah,
Okay, so once we have this basis, what do? We have a basis already. We can choose our trial function, right, and our test functions from this space that is spanned by these special functions that are built on Legendre orthogonal polynomials. What do we do now? We combine them. How? Well, we can write our trial solution and our test functions exactly the same way we have done it in 𝑓EM. Yes, yes. Wasn't a tricky question. So now, that is exactly what we do. But before that, let's look at pseudocode. Look how easy it is to compute those functions, right? So this is the function that computes a Legendre polynomial, right? Remember that is a recursive function. So whenever p, let's say, is quadratic, cubic, and so on, we get into this branch of the code, right? And so I'm calling this function again. That's why it's a recursive function, right? It's calling itself. And obviously, if you don't have a means to finish the recursion, then you get into an infinite loop, right? You just have to break the program in order to get out of it. And so these are the two cases that finish the recursion. Okay? So very simple function, very straightforward way to compute the Legendre polynomial. And now, well, I have a hierarchical function that is basically building the shape functions that I'm going to use. And so, very straightforward. I have the linear shape functions, and I know that at the very least I'm going to be dealing with a linear function, and so I just compute them, right? And only if the polynomial interpolation order is greater than or equal to 2, quadratic or further, then I have to compute all these expression as we saw the equations earlier. And so now notice that I return not only phi, but I am also returning the derivatives. So in the project, when you go to the next item after dealing with 𝑝-FEM and the quadratic 𝑝-FEM, right, then you're going to be implementing 𝑝-FEM. It is essentially translating all of this stuff in the code. So now your shapes functions, remember that shape funs.py file that we have been working with? In that file, you're going to write this new hierarchical function that is going to be giving you back the shape functions and the derivatives of the shape functions for 𝑝-FEM. Okay? But there is a little trick, and I will try to talk to you in the practical sessions so that you understand how easy it is to implement 𝑝-FEM if you know the right trick, right? Because as we will see, there are no nodes anymore, right? So in 𝑝-FEM, we always associate a shape function with a node. Why is that? Because the function has a value of 1 at the node, right? Although now that function is actually, if you think about it, it is non-zero in 2 elements. We always associate a function with a node. But what is going on here? Now, let's take a look, for instance, back at these shape functions here. Okay, say I associate that function with this node, and I associate that function with that node. Okay, so let's take a look at the quadratic one. You would associate that function with what? Huh?
Both 0 at the nodes.
Which node you would associate it with? Which coordinate?
One in the middle.
Well, let's take the one in the middle, all right? Let's say, well, why? Well, because I know that the value is minimum at the middle, at the other 2 nodes is 0, so let's take the middle. Right, so now I have one function that is associated to the node on the left, and another one associated to the node on the right, and I have now one that is associated to the center of the domain. Okay, let's take now this guy.
Oh no.
Huh?
Oh no.
Which one?
I said oh no.
You said what?
Oh no.
Oh no, you said oh no, yeah. So now I have 2 choices, right? What, this or this? And how about this one? Well, maybe this one, but this one was already here. So what you quickly see is that the notion of a node makes absolutely no sense anymore, right? And so we are no longer dealing with nodes per se, the way we think about them in 𝑝-FEM, but we are going to be dealing with generalized coordinates or generalized coordinates. So in a way, I can say that this whole function, it doesn't really matter which point I associate that function with, because I know that the support of that function is the entire element. You understand? And the same happens with all the other functions. Except, of course, for these ones, that as we discussed, they still hold this Kronecker delta property if we only look at the linear shape functions. Anyways, and so there is a trick on how to think about changing the implementation that you have in order to accommodate for artificial nodes, right? Artificial nodes, so that your element freedom table, right, makes sense in the 𝑝-FEM setting. And we're going to discuss that in the practical session. Anyways, so with the basis determined, as we said, well, we can now express our trial solution on our test functions in exactly the same way we have done it, right? Only now that this I, this index belongs to n, right? And that is the set that contains both linear and nonlinear shape functions, right? So it's a bigger basis. Right? So when I want to express, for instance, my trial solution in one element, and let's say that, if you remember, in matrix form, it was phi vector or row vector multiplied by u column vector. And the size of phi was for a linear element. What is the size of the vector? 2. It was a 1 by 2 vector, right? Okay, now let's go quadratic. 1 by 3. And if we go cubic? 1 by 4. And if we go quartic?
1 by 5.
And in general, if we go p order, that vector is going to be of p plus 1. And that is the only change that we need to do, in addition to the change that we just discussed, so that you get your element freedom table properly. Right? That is the only change that you need to do in the code. You're going to be dealing with higher dimensional shape function vectors. And of course, if the shape function vector has a higher dimension, well, obviously the strain displacement matrix is also going to have a higher dimension, right? But that is essentially the only case. So when we replace those two in our statement of the Galerkin projection, right, the weak form of equilibrium, now we get exactly the same system of equations Ku equals F. It's exactly the same process. It's just that now we are dealing with not only the linear functions, but also the nonlinear functions. But the rest is pretty much the same. So we obtain our Ku equals F system that now is hierarchical. And that is very important. So if you are very careful in the way you define your degrees of freedom, and then you say, for instance, that now I want all my linear degrees of freedom to come first, right? And then only the quadratic degrees of freedom, and then only the cubic, and then only the quartic. What you are essentially doing is you are making this K matrix hierarchical. So in the top left part of your matrix, you're going to have everything that is related to the linear part, and then there is a layer that is related to the quadratic, and then cubic, and then quartic, and then so on. So you can do this. And this is beautiful because imagine if you assemble the whole system for p order 10, for instance, right? And then you have assembled and you have your system of equations, and the structure is kept hierarchically, right? You can think about it, and you can slice that matrix and then solve for different polynomial orders, which is amazing because you assemble your system only once, and then you just keep solving for different polynomial orders just by simply doing a slicing of your matrix. Super nice. Anyways, well, as we discussed, we normally get the global arrays by assembling the contribution of local arrays. So if we're now at the element level, so let's see what happens at the element level E that has coordinates xi, xj, right? Now recall we just talked about it. My phi is the array of non-zero shape functions that now is going to be a p plus 1 dimension array. And so when I plug that into my stiffness matrix, right, and I'm going to change the integration domain, because we recall that my integration rules are defined in the -1 + 1 domain, right? Then because of this change of integration domain, I have the Jacobian popping up here, and then I have this dxc, because dx is just j dxc, right? We talked about it a few minutes ago in the lecture on isoparametric formulation. Remember that we also have these guys that pop up that are the inverse of the Jacobian, just because I am applying the change rule, right? Because remember that I'm interested in the end in the derivatives of the shape functions with respect to the physical coordinate, right? That is the reason why these guys pop up, because of the change rule. And then that is going to become equal, and I didn't say approximately equal because we are dealing with polynomials. And in this particular case, I'm going to keep my Jacobian constant. That means that the mapping I'm going to be using is the Jacobian, the geometry is going to be kept linear, which makes this formulation subparametric. Very well, guys, very well. So now I'm dealing with a subparametric formulation. So these guys here are going to be higher order, right? But the Jacobian is still going to be the length of the element divided by 2, and so the inverse of the Jacobian is 2 divided by the length of the element, right? So all of that is going to remain constant. I am using a subparametric formulation, and that is why I say this whole thing is equal, because I know I can integrate. So obviously, when we go to higher dimensions, I have to be careful with what? The only thing that changes so far from your code on ℏFEM is that now we are dealing with higher dimensional arrays in the integration, but what else do I need to change? I want to make sure that this is an equal. What do I have to change? The number of Gauss points, right? Because we know that n integration points integrate exactly a polynomial of order of 2n minus 1. And so I have this guy here and this guy here, right? So those are the derivatives. So when you multiply the derivatives, you're going to get the order of your polynomial that you need to integrate exactly. And that is what is going to determine the number of integration points that you're going to be using. Otherwise, you are using sub-integration. That is not good. Well, that is not good depending on the case. There are some situations where reduced integration actually helps you, right? So for instance, it is well known that your quadrangular element is too stiff in 2D, and so someone just by mistake produced a reduced quadrature rule for that element, and they figured out that the element was no longer stiff and was behaving more or less okay, and that is the so-called now reduced integration Q4 element, right, that you can find in your Abacus software or in other softwares as well, right? That was an accident, but it turned out to be working because it reduced. Now the element doesn't lead to locking for some problems. It leads to other issues like zero energy modes and yeah. But in any case, what I'm saying is that you do want, at least in this setting, in 1D, you want to have exact integration. Yeah, you have a question?
When we're integrating our P vector, do we use the same number of Gauss points for every order?
That is a very good question. And normally we do it like that. Normally we say, well, I'm going to just take my highest polynomial interpolation order, right? I know that the matrix that I'm going to be building is essentially a hierarchical matrix because I have all the orders there, right? But I need to integrate it exactly. So I'm going to pick the highest order that I need to integrate, and I'm going to choose a number of Gauss points to integrate that term. But that is really not the best way to do it, right? So as I told you earlier, at some point, the way we do it element by element, it is really not the most efficient way to do assembly. So you may argue, well, let's take a look at the 1, 1 term of my stiffness matrix. Well, I'm pretty sure that term is linear, right? So how about I just look at that term, I choose the number of integration points that I need to integrate that term, and I do the integration for my 1 million elements at the same time. Isn't that more efficient? Yeah, it is more efficient. So there are better ways to do this so that we can save computational time. Huh?
Can you explain it again? Sorry.
Yeah, so if you look at the stiffness matrix, the local stiffness matrix, we're going to have many, many orders, right? So instead of taking a look at one element and doing the integration of the local stiffness matrix for that element, right? And then picking up the higher order polynomial to pick the number of Gauss points that is going to integrate that term exactly, which means that I'm basically wasting energy in the other terms that have a lower polynomial interpolation order, right? Instead of doing that, how about I just pick the first term of my matrix, for instance, that I know is linear, right? And then I use only the number of integration points that I need to integrate a linear term, right? For my 1 million elements. Well, in fact, the linear, if I'm dealing with a stiffness matrix that is not linear, is even constant, right? But you see the concept. You pick one element of your stiffness matrix, and then you know how many integration points you need to integrate that order, and then you do that for the 1 million elements of your mesh. So that would be more efficient way to do this. Yeah.
Can you solve each polynomial order separately?
If I can solve each polynomial order.
You construct a stiffness matrix for each order polynomial, and then.
Yeah, but that's what I discussed, right? So if you have your stiffness matrix assembled, and you keep that hierarchical structure, right? Then you can simply slice and solve for p equals 1, and then for p equals 2, and then for p equals 3, and so on.
And then you just add them up because they all have the same source vector, right?
They have the same?
The same source.
Well, the source is going to change depending on the polynomial order as well. As you see here, let's take a look at the source, right? Because it's right here. So the final expression for the stiffness matrix looks like this. But now let's look at the force vector. Well, this guy is going to be also higher dimensional, but also higher polynomial order. So it's going to have linear shape functions and then quadratic, cubic, and so on. So depending on this guy, if that is a polynomial, then I have an exact integration. Otherwise, if it is not a polynomial order, if it is not a polynomial like in the project, then you're going to have to compromise, right? So you're not going to be able to integrate it exactly. So you're going to have to find a strategy to integrate that to the degree of accuracy that you're happy with, right? But notice that my source term, my right-hand side, my force vector, is also going to change depending on the polynomial order. So what I meant by slicing, obviously you have to slice your K matrix, but you have also to slice your right-hand side in order to solve for that particular degree. But the good thing is that you can do the assembly only once and then apply this strategy to solve for all the polynomial interpolation orders, as opposed to, okay, now I have to solve for p equals 2, let's assemble everything again for p equals 2. Right? Which seems to be a waste of resources. Okay. Well, we talked already about this. Now we are using a subparametric formulation since geometry is still interpolated linearly, and that's what I mean by these guys here. Those are still going to be constant. And so let's take a look at an example just to see how this is going to work out. So imagine that you have a discretization. You have 3 elements. And now in this discretization, I have p equals 1 on the first element. And you see that I only kept my linear functions. And then I have p equals 2 and p equals 3 on the other 2 elements. Can I do this? Yes. Why not? Why? Why I can do this?
Why not? Because all elements are independent?
No.
Because the support is only in the element.
There you go. The support is only in the element. More specifically, I can do this in the one-dimensional case because the nonlinear functions are exactly 0 at the nodes. So I don't have any gaps in my approximation. I still have what we call a p-conforming discretization. Now, this is the case only in 1D. That is what I said earlier, that there are some caveats that we need to deal with when we go to higher dimensions. In 2D, this is no longer going to be the case. And if we're not very careful, we can have gaps or non-conforming meshes, right? And we have to be a bit careful about that. But in this particular case, yeah, I can do that. I can have this element here, polynomial order equal 1. Here is 2, and then here's 3. So let's take a look how the approximation would look like. The approximation in the entire discretization can be written like this. So I have 7 shape functions, and obviously I have 7 degrees of freedom, right? phi1, u1, all the way up to phi7, u7, right? I can write it like this. I can say, well, this is going to be the sum of 2 terms, right? The first one is going to be comprised of only the linear shape functions. And notice, as this is a hierarchical approach that is building on top of 𝑝-FEM, then that's why I say here, this is my linear 𝑝-FEM term. And then this one here is my nonlinear approximation. I actually like very much writing the 𝑝-FEM approximation this way, because you could consider 𝑝-FEM to be already an enriched formulation, where we are actually enriching the linear basis with nonlinear polynomial functions in order to improve the accuracy of the formulation. And, well, is that good? Well, it really depends on the problem, right? Again, due to our Sea's approximation theorem, right, if whatever we're adding is going to be useful to reduce the error, because we know that the error is going to be orthogonal always to that space we're using, right? If whatever we're adding is going to be useful to reduce the error, well, the Galerkin projection is going to assign non-zero coefficients that are now called generalized degrees of freedom, right, to the nonlinear polynomial functions. Okay, so let's look at what happens at 2 nodes in this mesh. So if I want to evaluate the field at node 2, right? So basically I am right here. I know that all functions are equal to 0 except for phi2. And so phi2 evaluated at x equal to 2 is equal to 1. Remember, the linear functions are still satisfying this Kronecker data property. Only the linear functions, taken separately, okay? And so that is going to be equal to phi2. But let's see what happens. So the linear degrees of freedom, right? So the main message here is that my linear doves keep the same physical meaning as in 𝑝-FEM. Before in 𝑝-FEM, we said my degrees of freedom are going to physically represent the displacement field. Well, in the 𝑝-FEM, because we are building a hierarchical basis where the linear shape functions are not touched, right? My degrees of freedom associated with the linear shape functions are still going to keep their physical meaning. So now my U2, degree of freedom, represents the displacement or the temperature at that location. So they keep their physical meaning. Now let's take a look at this point x prime, which is basically x3 plus x4 divided by 2, right? Which is somewhere here at the middle, right there, right? Well, if you evaluate those functions, well, I know that phi3 is equal to 1/2, and this phi4 is equal to 1/2. And I know that in that particular case, this guy here is going to be equal to 0. So this phi7 function is equal to 0. So that goes away. And then I have another one. This function is non-zero. So notice that now we are no longer having this partition of unity property, right? Because all the shake functions right there, the sum of all the functions are not equal to 1 anymore, because these two alone are equal to 1. So I'm adding something that is going to change that, right? But more importantly, I cannot associate that U6 to be the displacement at that field anymore, right? I cannot do that. So U6 no longer has the physical meaning of the primal field, and that is basically the change from 𝑝-FEM. In 𝑝-FEM, the degrees of freedom, and keep this always in mind, the degrees of freedom that are associated with higher nonlinear polynomial shake functions no longer have the physical meaning of being the primal field. So they are no longer the displacement, they are no longer the temperature at that location anymore, right? Okay, well, they are more related, we say, to the derivatives of the field, because you can say, well, if I now take the second derivative of the field, right, then I get basically this expression, the linear functions go away. So U6, you could say that is more related to the derivatives, right? That's what we normally say. Okay, that's one example, and I also wanted to discuss briefly this example. We still have some time, just to show you how things are going to look also in the project, right? Because this is essentially what we are going to be doing in the project. We're going to obtain convergence rates. We're going to see how 𝑝-FEM behaves for smooth problems and for problems that are not that smooth. We want to see how the method performs. So it says here, use 𝑝-FEM with polynomial orders p, 1, 2, 4, 8, 16 on a mesh of 4 equally sized elements. Create a convergence plot of the relative error in energy norm, that is defined like that, as a function of the total number of degrees of freedom. Notice that now my convergence plots are going to be based on the number of degrees of freedom, because the concept of h is meaningless, right? If I keep my mesh fixed, well, all my elements are going to have the same h, right? So if I want to see the effect of adding polynomial, higher order polynomial shake functions, well, I have to plot that versus something else, and that something else is the total number of degrees of freedom. And that makes a lot of sense, because the effort that is needed to solve my system of equations is directly proportional to the size of the matrix, right? And that is the total number of degrees of freedom. Compare results with those of 𝑝-FEM, and also compare the condition number of the stiffness matrix computed as this form, where lambda max and lambda min are the maximum and minimum non-zero eigenvalues respectively. So if you remember this problem, we looked already at this problem. So it's like our infinite dimensional or semi-infinite dimensional bar that is basically in the ground and is constrained laterally by the same term that is a constant spring, right? And so remember that if I try to pull out the bar like that, then that constrained, it is constrained so that the force that I experience is in the other direction, right? We look at that, and we had an analytical solution for this problem, if you recall the first lecture. And so it's nice to revisit that problem. So when we look at the stiffness matrix, just because of the effect of that spring constant, we have this extra term that pops up, right? That is the only difference so far with respect to what we have been looking earlier. And again, the integration of my local stiffness matrix, is it going to be dictated by the highest term here or the highest term there? The second one, right? Because this one has the derivatives, and so I have to be looking at the terms in that second term in order to determine what is the element of that matrix that is going to require that is going to have the highest polynomial order. And so when you do that, you compute your K equals Ku equals F, and these are essentially your results, right? So what you see here in green is 𝑝-FEM, right? And you compare that with �Հ_FEM, and what you see in �Հ_FEM is that, well, �Հ_FEM behaves, the convergence rate, so remember, this is error, relative error in energy norm, plotted as a function of the number of degrees of freedom. So as we are going in that direction, we are increasing the accuracy, the number of degrees of freedom, indeed, for 𝑝_FEM. And what I am increasing in �Հ_FEM? The number of elements, right? That's why I go to the right is more accurate. But you notice that �Հ_FEM is really, really, really bad, right? I mean, it's not bad. It's just that what the method is able to do. That's the best it can do, right? So, but you notice that the constant, the slope of that line that is really a line in a log-log plot is actually constant. That is what we call the convergence rate, right? And so �Հ_FEM converges very, very slowly, whereas 𝑝_FEM, right? This is p equals 1, and obviously it's p equals 1 because how do you know it's p equals 1 that point? Well, it's exactly the same as �Հ_FEM, and it has to be exactly the same because remember that 𝑝_FEM is built hierarchically on top of �Հ_FEM, and so I know that for p equals 1, it has to have the same value. It has to be the same as �Հ_FEM. But this is p equals 2, this is p equals 3, this is p equals 4. And you can see that the error drastically reduces, right? This is what we call exponential convergence. And we're going to be looking at these concepts very, very detailed in the next, in 2 lectures from now, okay? Something else that you see, right, is that at some point, this is no longer decreasing. It kind of flattens. Who may have an idea what's happening there?
Numerical precision?
Yeah, we're hitting numerical precision. But why? Why are we hitting numerical precision? Are you not hitting numerical? Are you not working with 16 digits of accuracy? And 16 digits, I'm at 10 to the minus 8, right? So what's happening? Well, it turns out that the way we define our relative error in energy norm, we're just taking the square root of a number. The moment we take the square root of a number, we basically chop our precision by half. So that is what's happening. I'm just reaching numerical accuracy. And so maybe if I just plot the error square, then I can go in a higher precision and I don't have that flattening out. Another thing that you can see in this curve is the condition number. So here I am again plotting the condition number defined by the ratio of the maximum to the minimum non-zero eigenvalue as a function of the number of degrees of freedom, right? And once I want you to see or to notice what happens with the condition number for �Հ_FEM, which basically increases, right? It's a quadratic increase. So it increases quadratically. So the order is of nd to the power 2. If I plot this versus h, right, it's basically h to the power of minus 2. So if I plot here h, this curve would be in that direction. Okay? But notice what happens with 𝑝_FEM. It remains constant, and that is insane. Why is it? Why is that the case? Who can say it? Why it remains constant?
Orthogonality.
Yeah, because we have defined our shake function so that their derivatives are equal to the Kronecker delta property. That gives you the best possible condition number in the stiffness matrix. It cannot get better than this. And again, I have to say that this is only the case in 1D, all right? When you go to higher dimensions, condition number is not going to be so friendly for 𝑝_FEM either. Okay, so in higher dimensions for �Հ_FEM, we can expect still to see something that increases h to the power of minus 2. But in the case of 𝑝_FEM, it's not going to remain constant. It's going to be very bad for some polynomial orders. Still, the objective is to find the trade-off between your accuracy, right? The accuracy that you want to get for the amount of resources that you are willing to spend in obtaining the solution. You have a question?
Yeah, how do you compute the eigenvalues for very big matrices? Is it the same way, or is there a special way?
We are not computing eigenvalues here.
We don't need the definition.
Well, there are,
Can you hear the graph?
yeah, so for the, okay. The computation of eigenvalues is actually a tricky business, right? It is not cheap to compute eigenvalues. So, of course, you have different ways to compute eigenvalues. Normally, when you're dealing with big problems, we have these methods that are called subspace iteration methods that are not computing the eigenvalues of the original problem, but a reduced problem, right? Sometimes we're happy with the values that we get. But for the project and for the purpose of this course, all I ask you is just to compute the eigenvalues of the full dense matrices in the end, because that is going to be simpler, right? Otherwise, we have to really be careful, because again, when you are using subspace iteration methods, they are not really the eigenvalues of your original system, right? And so you can say there are also rules of thumb. Some people say, well, if I want to have the first few eigenvalues with high accuracy, then I have to compute the first, I don't know, n number. I cannot give you a number on the top of my head. But for the project, right, and so that you can show these plots, you basically transform your matrix into a dense matrix, and then you just ask NumPy x, and that is going to give you all the eigenvalues of the matrix. So you take the maximum, the minimum, and then you divide those two. Okay, and you don't have zero eigenvalues because you have constrained the problem, so you remove the singularity from your problem. All right, any questions? We are on time. All right, guys, we're done with 𝑝-FEM in 1D. The next lecture, next Tuesday, we're going to look at 𝑝-FEM in higher dimensions. But I hope to see you this Friday for the next practical sessions. Please keep in mind, let's try to get to the quadratic Lagrange chain functions results, at least, okay? See you Friday.